Now we're into the part of the course where things get a little more abstract. We want to give you a definition of a real vector space here. So here we go. This is taken straight out of our book. And I didn't really want to write it all down. So here we go. Let V be an arbitrary non-empty set of objects on which two operations are defined. We call them addition and multiplication by scalars. By addition, we mean a rule associating with each pair of objects, u and v, another object, u plus v. We just denote the operation with a plus sign. It's called the sum of u and v. And by scalar multiplication, we mean a rule associating with each scalar k. Scalars are real numbers. And each object u in v, a new object called ku. This is called scalar multiplication. If the following axioms are satisfied for all objects u and v, w in the set V, and all scalars k and m, then we call V a vector space, and we call the objects in V vectors. So here's 10 things that have to happen in order to be a vector space. First of all, the way you have addition defined has to actually be closed. This is called, number one here is called closure of addition. So that if you take two objects in V, you create this thing called u plus v. Is that still in the vector space? Yes, it has to be there. Number two is the commutative property. Number three is the associative property. ASSOC. Number four, there is an object in the vector space which we call the zero vector, such that 0 plus u equals u plus 0 equals u for all u in the vector space. That is, we have an additive identity. Number five, for each u in V, there exists an object which we call negative u, also in V, called the negative of u, such that u plus negative u equals negative u plus u equals 0. Addition's commutative, so you don't really have to say both of those. But anyway, this is that we have additive inverses. Number six, if k is any scalar and u is any object in V, then ku is in V. This is closure of scalar multiplication. Seven, there's a distributive property of scalar multiplication over vector addition. Distribute scalar multiplication over vector addition. Vector plus, right? Vector addition. Number 8 is also a distributive property, but now the things that are being added here are numbers. Where these were being vectors added, these are numbers added. So this is actually scalar multiplication over real addition. This is a distributive property of scalar multiplication over real addition. Number 9, this is an associative property of scalar multiplication here. And number 10 is that 1 times u equals u. That seems kind of crazy to have to say that, but we want this to be true. I'm not saying anything that wasn't already there. But in the world of abstract algebra, there are different types of things. There's groups, rings, fields, vector spaces, algebras. There's all sorts of things. And they have differing numbers of axioms that you start with. Essentially, if you have the first and the third, then you have what's called a semigroup. If you have the first, third, and The fourth, you have what's called a group. If you have 1, 2, 3, and 4, you have what's called an abelian group, and it builds up from there. So it seems kind of odd to me that the first step we take into the world of abstract mathematics is to go do it with vector spaces, which have 10 axioms. This is a fairly complicated structure, but this is what it is. This is a vector space. We should point out that Rn satisfies this definition. The way that we take objects in Rn, either think of them as directed line segments or think of them as n-tuples, the way we have it defined so that you add them and multiply by scalars satisfies all 10 of these axioms, and so Rn is a vector space. Check, it's a vector space, right? But there are other things that are vector spaces as well. And let's use the next video to look at some examples.